Mm, yeah, okay. Hello everyone. I'm Tong Chen from the Data Science Group from the University of Queensland, Australia. First of all, I would like to say thanks to Dr. Wan and all the organizers for the NeuRec workshop in ICDM 2020 for having me here to give this talk. So the topic I want to share with you today is called substitute recommendation, addressing personalization and interpretability. Uh, let's just start with a bit of background. Because I think Dr. Yao, Professor Yao has already given a very comprehensive overview on the functionality of recommender systems. So let's just have a brief idea on the relationships between different products in the recommendation scenario. So let's just take a look at a very typical online shopping process. So as a customer, when we are going for shopping online, usually we're gonna set a goal first. So whether we're shopping for sport, for food, or just for leisure, right? And the second stage would be to find the suitable candidates that we think will fulfill our goals. For example, when we are shopping for sport, we are probably looking for some different basketball shoes. So the third step is, of course, to narrow down all these candidates, all these options, and to make the final decisions. And of course, the last step in the shopping process is to check out and probably just to let your partner pay the bill. So with the product relationship in mind, a question we want to answer here is how can we help in this kind of intermediate users shopping process? So how can we let the users find better candidates more effectively and more efficiently? So that is where the product relationship comes into play. So, and there are two major types of product relationships. So the first is called a complementary relationship, and that refers to products that are complementary to each other. And those kind of complementary products are usually recommended as a bundle. So for example, we have the Apple MacBook, and we also have a keyboard. So they can be recommended as a bundle and usually have a slightly lowered price to promote the sales. And correspondingly, we are having the substitutable relationship between products. And in a substitutable relationship, it means products that are interchangeable or usually in a competitive relationship. For example, the iPhone 11 Pro, the Samsung Galaxy S10, the Huawei P30 Pro, these are all high-end cell phones made by different manufacturers, and these are all substitutable to each other. So this kind of relationship can be highly useful in the candidate generation stage, because if we can generate more high quality candidates for the users, it is more likely to observe a successful purchase from the user as well. So with that in mind, now let's take a look at the existing research work that has been done in regards to these two different kinds of product relationships. So first, for the complementary item recommendation, the target is very simple. It's just to recommend items that are mutually compatible to each other. And this is also known as bundle recommendation in a lot of scenarios. So it has two main purposes. Complementary item recommendation can stimulate further purchases after a user has bought a compatible item. For example, after purchasing a cell phone, it is very natural to consider buying a cell phone case to protect their phone. And the second purpose is to attract the potential customers via bundle advertisements beforehand. For example, it is very common to see some retailers to bundle cell phones and AirPods, so they can probably have a promotion effect on the sales. And we have seen diverse applications in regards to the complementary item recommendation. For example, we have the fashion recommendation, so to search for a set of clothes that can match up with each other, and targeted advertising in the e-commerce world and online retail as well. Well, now let's take a look at what's happening in the substitutable product relationship. Well, we have to say, compared with the complementary product relationship, the study on substitutable product relationship is largely unexplored. So for substitutable product recommendation, we usually want to recommend items that are substitutable or even superior to the one that is being viewed by the user right now. So this can have two major benefits. So it can expand the user's view to make a better decision, right? And secondly, recommending more substitutable products can eventually increase the chance of a successful purchase because we are naturally getting more options to choose from. So there are, of course, some closely related research in this regard. So as far as we can recall, the first systematic work working on substitute recommendation is called SEPTURE. And it uses the LDA, which is a topic model, to learn the representations of items. So the items are modeled by the topic distributions and their compatibility or substitution relationship can be easily captured. And there are some other methods using textual features as well, because the SEPTURE is the text-based model. For example, we have the relation-aware recommender network and the linked variational autoencoder. These are two neural network-based extensions of the text-based models for substitute recommendation. And in some recent research, we have also seen a lot of graph embedding approach. For example, the path-constrained model, the PMSC, and the SPEM. These are two deep neural network embedding methods. So they aim to model the structural information in the observed product co-occurrence graphs. For example, in the Amazon dataset, we are usually having those also view the relationship between two interchangeable products. Well, with that said, the question we want to ask here is, are these methods good enough, right? Can they solve all the problems in substitute recommendation tasks? Well, of course, no, because we are doing research here. So we naturally identified several unsolved problems of existing substitute recommenders. So one thing comes from their problem definitions, and here is it. So their problem definition is, given a query item V, the model will retrieve k items that are substitutes for item V. So we can see that the user is completely neglected in those methods. So the consequence is the recommended substitutes are not personalized for any kind of users or any specific users. So with the same query item V, the retrieved k items are only subject to their similarity to the query item V. And all different users will get the same set of recommended items if the same query item is used. And the second drawback is more severe in current research trend, because most existing substitute recommendation models are purely built upon latent vector models, like the Word2Vec or the deep neural nets. So there is a natural consequence for this as well, because the interpretability of those recommendation results is very low. So it's going to be very hard to convince a user why the recommended substitutes are more suitable than the query item and how they meet this user's specific needs. That means comparison on different attributes is needed. So for example, if we are searching for a car to buy, if we want to take the car for our daily use, we're going to care about different aspects. For example, we care about its build quality, we're going to care about its design, and we are going to care about its running cost. So comparison among those different but small attributes are very important for substitute recommendation. So that kind of summarizes our motivation for this research, which is unleashing the power of personalization and interpretability in substitute recommendation. So here is our slightly revised problem definition. So given a user item query, U and V, the model is going to retrieve K items that are substitutes for item V. That's the first requirement. And the second, they are of interest to user U as well. So that's for personalization. And we also want the generated result to come along with some textual explanations to ensure the interpretability. So this is a kind of a simple demonstration of what the ideal personalized and interpretable substitute recommendation looks like. So for example, we have two users, Alex and Bella, and they both come across the iPhone 11 Pro when they are searching for the new cell phone to buy. And for Alex, he is much concerned about the camera performance. So the recommended substitutable items are other cell phones with high performance cameras. But things are a bit different for Bella because she is just a fan of Apple. So the ideal recommendation results for substitutable products would be other cell phones also manufactured by Apple, and that will fulfill her personal preference. So let me just briefly introduce one solution proposed by our group. And this is a CIR 2020 paper, and it is called "Try This Instead: Personalized and Interpretable Recommendation on Substitutable Products." So our solution is called Attribute-Aware Collaborative Filtering, or ATCF in short. And the key driver for our solution is the growing availability of user reviews. Because we can see that the user reviews offer a lot of information apart from the different aspects that a user may care about when doing the purchase. It also contains semantic information about the user's feedback, whether the aspect on this item is good or bad, something like that. So there are some benefits of using the attribute for collaborative filtering. And we want to decouple the user item interactions into two parts, which are user attribute and item attribute interactions. So it is worth mentioning that our solution is also motivated by a lot of preliminary studies. For example, the collaborative filtering, especially the neural collaborative filtering, and also the collaborative filtering based explainable recommendation with textual information, like the explicit factorization, the EFM. So here we present some details about our solution, ATCF. So the intuition of our model is kind of easy to understand. So based on users' reviews on different items, we can directly construct the two kinds of matrices using some sentiment analysis tools. For example, we can have the user attribute matrix, and we can also have the item attribute matrix. And if we do factorization on both matrices, we can learn three types of representations. We can learn the user representations, attribute representations, and also the item representations. So we are actually using the attribute representations to bridge the user's preference and the item's substitution relationship for our substitutable recommendation task. So of course, the first step is to build these two matrices, X and Y. So we just directly apply a well-established tool named the standards because our technical contribution doesn't lie here. So we just use off-the-shelf tools. And for each element in the user attribute matrix, it can be viewed as a summarization of all of one user's sentiment towards an attribute of an item. And for item attribute matrix, it can be viewed as a kind of crowdsourcing overall score from all the users to a specific aspect of one item. And that's it. And with X and Y matrices constructed, we can easily perform some collaborative filtering. And the collaborative filtering framework we have chosen here is the neural collaborative filtering framework here. And I think most of you are probably very familiar with this. So it's just gonna predict all the entries in both matrices, and we use the mean squared error to optimize this entire framework. So after this, it's time to estimate the missing entries in both X and Y matrices. So I'm gonna briefly introduce the contexts carried in those matrices here. So for the X matrix, if we see each line as the xi here, so each element actually means one user's preference on an item attribute from A1 to A6. This is just an example. So for the estimated Y matrix, if we take one row, that actually means this item's quality on each of these 6 different attributes. Of course, in the actual data sets, we are having more attributes than that. So here comes another question. How can we utilize those estimated X and Y matrices for personalized and interpretable substitute recommendation? Well, here comes to the core step of our A2CF model, which is uniting the substitution and the personalization constraints for recommendation. So here we use a modified version of the Bayesian personalized ranking, the BPR loss, because we want to imply both constraints on the recommendation results. So we have defined a triplet scoring function here. So the first term here is the substitution constraint, and the second term is the personalization constraint. And the gamma here is just a trade-off parameter, which is just a hyperparameter to be tuned. So the new BPR loss can be written in this way and can be optimized by sampling the positive samples as well as the negative samples. So the fifth step is to actually implement it. We need to implement the actual scoring functions. So here, for both constraints, we formulate each item as a weighted sum of all the attributes. So we take two scaling factors here, the beta and epsilon. So they will control the degree of the attention strength for different distributions. Because we have now already implemented the recommendation part, another very important feature of our A2CF model is its interpretability. So how can we generate interpretations? So actually, after getting the users and the query items representation, we can calculate a kind of advantage index, something like this. So the xi is the attribute-wise user preference, and yj is the recommended item, the attribute-wise item performance vector, and yq is the attribute-wise item performance vector. To give you a better idea of how this works, here is a toy example. So just suppose we only have 5 attributes in the entire data sets: the price, screen, battery, camera, processor. So the yj is the recommended item, which we reckon is better than the query item. And they have corresponding scores for different attributes. So we take their subtraction at the first place, right? So we can get the direct comparison results on each of those 5 aspects or attributes. And then we do an element-wise multiplication with xi, where the xi means what the user cares. So each element has a score. So if the score is higher, that means the user is paying more attention to that attribute when doing the purchase. So after doing the element-wise multiplication, we can get the final advantage or disadvantage index. So the higher score means there are 2 conditions. So first, the recommended item is better than the query item on that attribute. And second, this user happens to care about this attribute when doing the purchase. So after that, things become easier. We only need to use the generated index to further generate some personalized interpretations. So here we use a template-based approach. So it goes like this. Well, based on the item you are currently browsing, we recommend you to try this one instead, because it comes with some adjectives and some attributes. So with the details presented, it's time to validate our model by doing experiments. So we use 3 large-scale datasets from Amazon, so cell phone, automotive, and office. And there are well-established rules for identifying substitute recommendations here. So I won't be elaborating on that in detail. And we compared that with 4 different baselines. So from the quantitative results, we can directly see that our proposed method is more accurate than all the baselines chosen in our experimental study. And here comes to another very important part, which is the interpretation. So to evaluate the interpretability of our model, well, we just can perform a case study on the interpretability. So we actually use A2CF to generate interpretations when doing recommendations. And for the users, we also directly copy their reviews from the dataset and compare 2 against each other. So let's take the first case as an example. So based on the item, this is a Samsung cell phone you are currently browsing. Our A2CF method recommends another substitutable item instead, because it comes with better battery better screen size and better chord. So to validate whether our retrieved attributes are actually concerned by the users, we compare that with the user's original review. So this is a correct recommendation because the user has actually purchased and reviewed on Amazon. So we can directly take his review to have a look. So this user says, I'm aging and eyesight is diminishing, and only this cell phone screen size is big enough for me to easily read, and that's a plus for the screen size. So that means the A2CF can accurately identify some important attributes for different users when recommending different substitutable items. So we also have studied a lot of hyperparameters in the A2CF model. Now, for example, the hidden layer size, the trade-off parameter gamma for that modified BPR loss, and two scaling factors in the attention mechanism. And we have also conducted some ablation study to verify the contribution of different model components as well. If you are interested in those details, you can have a look at our CIR paper. So it's now time to wrap up all our findings in this study. So our contributions made in this work are threefold. So firstly, we define a new problem. So the personalized and interpretable substitute recommendation, which can be very useful for both the industrial and the future academic research. And secondly, we propose the A2CF, which is a novel method for addressing this problem. And third, we have done some extensive experiments on large-scale datasets, and we have shown that our proposed method is superior in a lot of aspects. At the same time, I think I can summarize three future directions for substitute recommendation. So the first thing is that we can combine substitute recommendation with sequential recommendation. Because people's interest will change and they are gonna exhibit long-term and short-term interest when doing purchases online as well. And the second thing is we can elaborate more on the knowledge graphs to perform some knowledge-enhanced interpretation, so we can make our interpretation more high quality. And the last thing is we can bring more long tail items to users' view using the substitute recommendation scheme, because usually the popular items are preferred by most recommenders. However, there are still some interesting, valuable, or very cost-effective items that are long tail items and are unpopular items worth investigating for substitutable item recommendation. Well, so that is all for my talk today. Yeah, thanks very much.